Alright, hey everyone. So for our next lesson, we're going to look at the other type of mechanical energy that we have to be concerned about, and that is potential energy. Alright, so potential energy. A nice sort of simple definition for us is potential energy is just energy that is stored. So stored energy. And that's all it means. So you can store energy lots of different ways. Like you can store it in a battery. We're about to learn that you can store it using like height or some type of elastic band that you could stretch, or like a spring. And when you stretch it, like we know that we're storing energy in it, because once it's stretched all the way, what happens when you release it? It snaps back into place. All that energy gets released. So since there's energy there, we know it must have been stored in some way. And we just have a word for that in physics. It's called potential energy. So it's any type of energy that's stored. If you can store it in some way, it's potential. We're going to talk mostly about a specific type of that stored energy called gravitational potential energy. What this is just energy that is stored using height. Energy that is stored using height. So it's kind of a weird idea that you can store energy using height, but it sort of makes sense if you think about it. If you take an object like a pen, and you raise it upwards, you're actually storing energy in the object. And we know that we're storing energy because we know that we can release it. How would I release the energy in this pen? Well, I could just let go of it. And notice that as it falls, it gets faster and faster and faster. So it gains, I think we talked about kinetic energy on the other lesson. So if you can release energy, that means you must have been storing it in some form. So gravitational potential energy is just stored energy using height. The higher it is, the more energy that's stored, which is a good thing to write down. So you can store more potential energy. So you can store more energy by gaining. That says gaining height. So the higher an object is, the more potential energy there is. If you put an object twice as high, it has like twice as much potential energy. So the higher and higher and higher it goes, the more energy you store in it. And you can release that energy by letting go of it. And so it'll fall, or maybe if it's like a car or something, it could roll down a hill. So again, you're just storing energy in this sort of form using height. And it's energy that can be released if you let go of it. Let's answer some questions and try to work with this idea a little bit. So for 13, your friend wants to store his bowling ball on top of his bookcase. You tell him it's dangerous to store it there because it has a lot of energy. It should stay on the floor. He says it's not moving, it's not plugged into the wall, and it has no batteries, so it has no energy. Your best response is, okay, it has kinetic energy, you just can't see it. It has stored energy because of its height. It has internal energy. Or you're right, it has no kinetic energy. I would say that this is dangerous, and the reason it's dangerous is that bowling ball that's up really, really high, it does have energy, it's just that it's stored. So I'm going to say the answer is B. It does not have kinetic energy because it is not moving. But you could release all of this potential and turn it into kinetic if the bowling ball rolled off the shelf, and then it would lose its height, it would lose its potential energy, because that energy would turn into kinetic. Now it's moving. But for 13, B is a good answer for us. Alright, your friend, let's look at 14 now. Different type of potential we're talking about here. Your same friend keeps his crossbow stored on the table with the bow stretched back ready to fire an arrow. Seriously, stop going to this guy's house, he's crazy. He tells you that the crossbow doesn't have energy until it's fired, and your best response is... Okay, so crossbow, if you don't know what I'm talking about there, it's like a bow and arrow. It's kind of like that, and it's all stretched back and ready to fire. This is definitely dangerous. And he says it doesn't have any energy till it's fired. Your best response is? I would say that he's wrong. I would respond with, you're wrong. And the reason he's wrong is that the object does have energy. It has potential energy. It has stored energy. When you stretch back the bow or the elastic on the crossbow, you're storing energy in it. That's just waiting to be released if the arrow got fired. So it does have energy. It's just that it's that stored potential energy. Alright, and we got to be able to think about what's happening to our different types of energy as things happen to the object. So like 15, an elevator lifts its passengers upwards at constant speed. What's happening to the potential energy? Okay, so if we're going like upwards, we're gaining height, right? So I would say that our potential energy is increasing. Because again, as you gain height, as this elevator lifts you upwards, that's what this potential energy is. You're storing energy the further up you go. The car accelerates while traveling along a flat, level road. What's happening to the potential energy? So remember, this potential energy is related to the height of the object. The height of the object. And really nothing else. It does depend on the mass of the object, but the mass won't be changing. So again, we're going to really look at the height for this. So a car accelerates on a flat road. So if you're, a car on a flat road, you're just going on this flat road. Is your height changing? I would say no. And so what's happening to the potential energy? I think it's staying the same. In fact, since it doesn't have any height, right, the road is probably on ground level or on the ground, I would say that it probably just has no potential energy at all. It is accelerating, so it's changing speed, it's changing kinetic energy, but it is not changing its potential energy. Okay? So besides just talking about it sort of in general terms, we can calculate a number for this. We can calculate a number for this potential energy using our potential energy equation. It's a nice, simple, straightforward one, which is good. I mentioned this in the last video, but again, if you need any of your equations, they are all back here on the last page. So PE equals M times G times H. And just to have it in your notes, let's write down what everything stands for. I like doing that in different color, though. So whatever this is. So M is going to stand for the mass of the object, which, remember, mass we always measure in kilograms. G we've seen before. We saw it when we did forces, specifically the force of gravity. G stands for the acceleration. That says accel, A-C-C-E-L, as in acceleration, due to gravity. You may remember that on Earth, anyways, it always has the same value of 10 meters per second squared. I did give that to you on the last page, so you don't need to remember the 10, but you got to remember that you know it. So G is the acceleration due to gravity, and it has a value of 10. It's getting worse. Okay. Which leaves H. We said that potential energy is related to height, so H is going to be our height. In physics class, we're always going to measure height in meters. And then last up is PE, which stands for, you probably guessed it at this point, potential energy. The unit for potential energy, the unit for all of our energies, is going to be joules still. So kinetic and potential both have the same unit because they're both energies. They're both measured in joules. Alright, let's see if we can work with this idea a little bit. 17. The same ball is shown in 3 cases. How does the potential energy compare in each case? So we've got this ball, it's up here. So we can bring it to the top of this, thin sort of vertical thing, like straight upwards. Or we can move it up a hill. Or we can sort of zigzag it up some stairs. How does the potential energy compare? What I mean by that is, is A bigger than B, or is C bigger than, how do these compare? Alright, well, potential energy is mgh. If it's the same ball, I would say it has the same mass, right? So we know that m is the same. I'm assuming we're on Earth for all of these, because I didn't tell you otherwise. So g is the same. And let's talk about the height. Now, I know that they're brought up different paths, but if we look how high up they all ended, I would say that the height actually is also the same. So, how does the potential energy compare? It is the same in each of these different pictures. And I think the simplest sort of, with just 1 or 2 words here, the simplest explanation for that is they're all at the same height. And so they all have the same amount of stored energy. So it doesn't matter how you get there, as long as you end up at the same height, it's going to be the same. 18. An object has 0 joules of gravitational potential energy. What does that tell you about the object? Well, gravitational potential energy, that depends on the height, right? So if it has no potential energy, I would say that it has no height. And that's what it tells you. So it's like, oh boy, you could write a few different things here. You could say that the height is equal to 0. I would take that. You could have written, sorry, it's at ground level would be a good one. Anything that you write that would illustrate the idea that the object just doesn't have height because it has no potential energy would work. Alright, and let's get into a couple calculations. So we'll do 2 together. I'll have you try a couple on your own, and that would be good. 19. Calculate the potential energy of a 3 kilogram dictionary on a 2 meter high shelf. Let's go. We have, calculate the potential energy. We have an equation for that. And again, they are all in the back of the note packet if you need it. It's m times g times h. I think m is 3 because, right, mass is measured in kilograms, so that 3 kilograms must be the mass. G, always, 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 here on Earth, has a value of 10 meters per second squared. A 2 meter high shelf, well, it's, sounds like height, so we'll throw that in here. And sort of a nice, easy calculation to do in your calculator. No squares or anything like that, what we had for kinetic energy. 3 times 10 times 2 is, I got 60, and the unit, joules. So this book has energy stored in it. It's energy that would be released if it fell off the shelf. 60 joules of stored energy. 20. Find the potential energy of a 1100 kilogram car that is on top of a 17 meter tall hill. Alright, so okay, we've got an equation for that. So once we realize we're calculating potential, this seems like it'll work. Mass is measured in kilograms, 1100 kilograms. G is always, always, always 10 here on Earth, and then the height is 17 meters because it's on top of a hill. Alright, multiply all those numbers in your calculator or on your phone or whatever you have available. And I got an answer of 187,000 joules. That's a 0. And this is a J right here for joules. So I got 187,000 joules. It always is good to think about our answer here. When we looked at the dictionary, 3 kilograms is like 6-7 pounds, something in that neighborhood. And it's got 60 joules of energy, so it's not a whole lot of energy. This car, well, first off, it's a lot more massive, right? A car compared to a book. And it's on top of a really tall hill. 17 meters is pretty high up. And so since it's this big heavy object that's really high up, it has a lot of potential energy. Notice that this 187,000 is way, way, way bigger than the 60 joules. Which makes sense, because again, it's really heavy, it's really high up, so it has a lot of energy stored there. Okay, those are the ideas here. So potential energy is energy that is stored using height, and we have this equation for it, m times g times h. What I'd like you to do now is pause the video and try all of the problems on page 6. So that's this page right here, numbers 21 through 26. So 21 through 26. Some of these are about potential energy, some of them are about kinetic energy, which was the equation that we did on the previous lesson. So we're going to have to use both of those here. So pause the video right now, give all of these a shot. I'll give you, well, I'll wait a little bit for you to pause it. And try them, and I'm going to go over them all, so if you get stuck, just move on to the next one, and then watch my explanations when you're ready. Alright, so hopefully you tried them all at this point. Let's go over them. An 1,800 kilogram car is at rest at the top of a 10 meter tall hill. What type of energy does it have? Okay, well, it's at rest, and so one thing that we know is that it does not have kinetic energy, because it is not moving. It does, however, have height, so I would say that it has potential energy, because it has height, but no motion to it. So we have stored energy, but no, movement energy, we would say. When I say how much, alright, well, we have now that we know its potential, we have an equation for that. It's m times g times h. M is 1,800 kilograms. We're going to multiply it by g, which is always 10, and then times a height, which is actually also 10 for this problem. Alright, throwing this in the calculator, I got 180 1,000 joules of energy. Which, if we're thinking about this, I hope that seems like a big number. But again, it's a really heavy car. It's on top of this tall hill. It makes sense to be a big number. This little funky thing over here, that's a J for joules. Sorry about that. Alright, the same type of car is traveling on a level road, so it's a flat road, at 10 meters per second. What type of energy is this? Alright, we're on a flat road, so it sounds like we're just going to be like at ground level, right? So we don't have potential for this one. We are moving with a certain speed, and that does not sound like potential to me. That sounds like kinetic energy. So the answer to this one is kinetic energy. And when I say how much, we did learn an equation for it. If you forgot it, go to the last page of this note packet, and it'll be there for you. The equation is 1/2 times m times v squared. Plugging in 1/2 times the mass is 1,800 kilograms. Oh, I think I put an extra 0. 1,800 kilograms. And it's moving at a speed of 10 meters per second, and we're not going to forget to square it, right? Because that has to be there. Okay, throwing this in a calculator, it gave me an answer of, I got 90,000 joules. There we go. So an important recognition there, that if it's moving with speed, that's kinetic energy rather than potential. But once you get that, it's just using the other equation. Alright, car's traveling up a hill at constant velocity. Alright, so there's a bunch going on here. I want you to tell me what's happening to the kinetic energy, the potential, and then we'll talk about C after that. So the kinetic energy is, remember, kinetic energy depends on mass and speed. The mass probably isn't changing. It's the same car, right? So the mass is not changing. Is the speed changing? I would argue that no, it's not, because it's a constant velocity. So it's moving at the same speed the whole time. I would say the kinetic energy is staying the same. Because constant velocity, it's not getting faster, it's not getting slower, it's moving at a constant velocity. The potential energy, well, if we go up a hill, then we're like gaining in height, right? When you go up a hill, you're higher up than you were. So I would say the potential is increasing for this problem. Would it be possible to do this without any gas in the tank? The answer to this one, hopefully you're thinking the answer is no, and it is. No, it is not. Because let's think about it like this. If you're gaining height, where would the energy come from? It has to come from somewhere. Probably, since you're driving a car, it comes from the gas in the tank. So anything, no, you need an energy source, right? You need an energy source. You need somewhere for all of that energy to come from, that potential that you're gaining as you climb the hill. 24. Car is moving on a flat, frictionless surface with increasing speed. All right, increasing speed. Now we're getting faster. And if we're getting faster, then the kinetic energy is increasing or getting larger. For potential, remember, that's related to height. It's a flat road. Flat road. So is its height changing? No, I don't think so. So what's happening with the potential energy? I think it's staying the same. Right? It's not increasing, it's not decreasing, you're not changing height, you're just on a flat surface. 25. What is happening to kinetic? What's happening to potential as a rocket flies upward with increasing velocity? I'm hoping you're sort of catching on to this idea at this point, that to figure out the kinetic energy, I'm just interested in the velocity. To figure out the potential energy, I'm just interested in the height. So for the kinetic energy, let's think about what's happening to the velocity, or the speed. It sounds like it's increasing, getting faster. So what's happening to kinetic energy? It's increasing. Because, again, I just told you that the velocity is getting faster, and that's how you'd know. For potential energy, remember, that's related to height. So if we're flying upwards, I think our height's going up. So our potential energy is going up. 26. The car is applying its brakes and slowing down as it moves down a slope. A lot going on here. Okay, so for kinetic energy, if there's a lot going on, I keep it this simple. Kinetic energy is how fast it's moving, or related to how fast it's moving. So, if it's slowing down, the kinetic energy is decreasing. Again, just because it's slowing down, that motion energy is getting lost. What's happening to the potential energy? All right, well, if we're going down a slope, then we're losing height, and so the potential energy is decreasing as well. So for all of those types of problems, for kinetic, just look at the speed or velocity. For potential, look at the height and figure it out from there. All right, and that's it for this lesson. For Friday, you're just going to do that worksheet. If you have any questions on it, please email me, and I'll be happy to help you out with it. And other than that, that's it.